Good evening, everyone. Myself Gautam Sharma. I welcome you all in behalf of Sapience Education. So we will discuss about phasor diagram of LCR, and we will also find so many terms in LCR or LC circuit, whatever you can call. In this circuit, we will get all the three types of resistance. So let us see here. So this is your LCR circuit, and here we will have a resistance, pure resistance, as well as inductor as well as capacitor. Let us consider we have earlier applied EMF. So while applying EMF, it means that we are getting a current as well as, okay. So we can write either equation of EMF or current. So both will have an existence, either you are writing or not writing. So let us consider the current. We now take with respect to the current. So current is equal to I naught sine omega t as a source of a current. So here when this current will pass, so what will happen, there will be a different sort of a voltage across resistance. VL is voltage across inductor, and VC is the voltage across this. So these are the maximum voltage drop. So we can tell here maximum voltage drop, maximum voltage drop we can tell maximum voltage drop as Vr, and Vr can be written as I naught into R, that is I naught is the maximum current, so maximum voltage drop is I naught R. Now if we talk about the VL, that is inductive voltage, so it can also written as I naught into resistance. So resistance for the inductive resistance is your XL, right? So we can write this. Now if we talk about the VC, so this is maximum voltage, so this can of the capacitive, maximum voltage drop of the capacitive across the capacitors, so it can be written as I naught into XC. So I hope you have understood this. Now we have already done that XL is equal to omega L and XC is equal to 1 by omega C. This thing should be understood, right? Now we need to represent it in a graph, so that phasor diagram. So let us represent it in a phasor diagram. So the phasor diagrams are as follows. In phasor diagram, first of all, we will take current as I naught. Okay. So in phasor diagram, see here, in phasor diagram, first of all, you need to take a axis as a x-axis as well as y-axis. So let us, I am taking here y-axis and as well as x-axis, right? Now if you will represent the current, so let us represent the current as I naught. So this is the current. So in this direction, let us consider this is the current. So I will not take omega t here. Why? Because I am taking omega t, the position of omega t here only, right? So let us consider I naught as this form. So earlier what we used to do, that I naught or omega t, we are taking omega t from this. Now we are assuming that this reference line here only, so that we can get a proper rearrangements. Okay, it is not like that is in not making an angle. So let us consider the line must be here only, from where we are taking a reference like this. So don't bother about this. So it is useful for the representation, right? So there is an I naught, so we can put here I naught. Now what about omega t, what about the EMF? So what about the EMF? So EMF for which one? So we will do it so see here, which EMF or which voltage is with the same phase. So we know that resistive circuit VR is in the same phase. So can we draw VR as in this direction? So let us draw VR. This is your VR. So this is a VR, right? This is your VR. So this is your VR, right? We can draw here VR. Okay, because it has same phase. Now what about VL? VL, that is inductive. So VL is in down, it is back lagging. So we can do here VL like this. Got it? So this is your VL, because it is lagging by 90 degree. Now what about a BC? BC is ahead so of 90 degree with the resistance or with the EMF, okay, or with the I naught current. So BC will be definitely in this direction. Let us consider this as a BC. Got it? So all are in the vector form. Now if we consider BL, this is your BC circuit. So if we consider that VC is greater than VL, so it may happen that VL may be greater. So let us consider. So I have considered VC is greater than VL. So net resultant voltage will be in upward direction because VC is greater than result. So this is your net upward direction. So net will be VC minus VL. So this one, and this is in this direction VR is there. See, vector addition for this part and this part has been done as BC minus BL. So this is VC minus BL. Now what about VR? So we need to take it. So we know that the vector addition, so if there is an angle, so the two vector which is perpendicular to each other, so when we will draw it like a parallelogram, so you will get a resultant, and this resultant voltage, this is a resultant voltage, right? Resultant voltage, that is E. Okay, so resultant voltage, this is a resultant voltage and it is making an angle of phi with the reference point. So we need to find a resultant voltage. Okay, so resultant voltage can also be written as E is equal to E naught sine omega t plus phi. Why? Because it is making an angle phi. Now we need to find a E naught. So how you will find a E naught? E naught. So this is a E naught, right? This is E naught because it is a resultant of the old voltage, that is maximum voltage. So maximum voltage can be calculated as how? So this is the vector addition. If you observe the vector addition, let us assume the vector addition. So this direction we have got BL minus BC, BC minus BL, BC minus BL. So it appears to be similar. So let us erase it properly. Erase it. Okay. Yeah. So this in this direction it is BC minus BL we have got. So BC minus BL, and in this direction we have resistance VR. Now in this direction we have mm, resultant voltage for this, that is equal to E naught. So for E naught, if you want to find E naught having an angle phi, so E naught is equal to, tell me, E naught is equal to E naught. So we know that vector addition for two vector A and B. So net resultant vector is equal to root under magnitude of net resultant vector is equal to root under A square plus B square plus 2AB into cos theta, where theta is the angle between vector A and vector B. We have here two vector, that is your this one and this one, and it is making an angle of how much? 90 degree. How you will find resultant EMF? So this will be VC minus VL whole square, A square, that is VR whole square, plus 2AB, that is VC minus VL into VR cos 90 degree. So this whole term will become 0 because cos 90 is 0. So finally we have got this as a VC minus VL whole square plus VR whole square. So this is the EMF equation. So E naught, if you want to find E naught, so you have to use this equation. Now we can also find in terms of resistance. So resistance, so E naught is equal to I naught into R, we can write. Not I naught into R, we can write here I naught into resistance of all the whole circuit. So let us consider, if E naught is the EMF for whole circuit, so Z is the resistance of LCR circuit, resistance of LCR circuit, and it is also known as, it is also known as impedance. Impedance, right? Now, before writing this, can we write here? Let us write here. Okay, just put the value. So from here, E naught. Why I am writing this? Okay, I should. Okay. Now this is equal to E naught is equal to Vc. What is the value of Vc? Just now we have done Vc is equal to I naught into Xc, VL is equal to I naught into XL, Vr is equal to I naught into R. So we will put each and every value. So when we are putting here each and every value, so what we are getting? Vc is equal to I naught into Xc minus VL is equal to I naught into XL whole square plus I naught into R whole square. Now when we take this, so we will get I naught as a common from each and everywhere. So we will get Xc minus XL whole square, Xc minus XL whole square plus R square, and this is equal to E naught. And why not we can write here E naught by I naught. So E naught by I naught can be written as Xc minus XL whole square plus R square. So this one is the EMF by maximum EMF in the circuit by maximum current, and this is known as Z, and it is known as impedance. So finally impedance can be written as root under Xc minus XL whole square plus R square. So this is the impedance equation. This equation is for impedance. So this is an impedance equation. So I hope you have understood this, right? So this is overall. This can be also considered as overall resistance of the LCR circuit. Resistance of LCR circuit. Right, so this is a overall resistance. Now the thing is that what is the phase difference, how much angle it is making, so with the current. So if you want to find angle that is phi, so we use the equation. So just here only I am just writing so that you won't get confused. So can we write here tan phi? If you observe this triangle, so tell me tan phi is equal to perpendicular by base. So this length and this length will be same, that is equal to Vc minus VL divided by VR. If you take out common similar to the current, so you will get tan phi is equal to Xc minus XL by R. This is equal to tan phi, and from here phi will be equal to tan inverse Xc minus XL divided by R. Okay, so this is the phase difference. Got it? So I hope you have understood. Now I will want to add one more thing, that is resonating condition. What is resonance? Resonance condition. It is the condition. It is condition when flow of current is maximum. Flow of current is maximum. Current is maximum. So what do you mean by maximum current flow? Let us consider Z is the impedance for the LCR circuit, and this is equal to Xc minus XL plus R square. Now if you increase frequency, so what will happen? If we increase frequency or omega, so what will happen? Xc is equal to 1 by omega c. So what will happen? If we increase, so Xc will decrease. So a capacitive current will increase. Now if XL, what about XL? XL is equal to omega into L. So omega is increasing, so XL will increase. So what will happen? Inductive current will decrease. So what happen? One is increasing and one is decreasing. But we want stable condition. So in stable condition, what will happen? This both current due to both will be equalized. It means that when XC will become XL, when Xc will become XL. So what is the value of Xc is equal to 1 by omega C, and omega this has a value omega L. So what is the best frequency so that we can get the maximum current? So Xc is equal to XL. So from here omega will be equal to omega square is equal to 1 by LC. So from here omega is equal to 1 by root under LC. So this is the resonating condition. Resonating condition for LCR circuit. And one more thing you have noticed here, that in this condition Xc is equal to XL, Xc is equal to XL, sorry, Xc is equal to, so from here Xc is equal to XL. If we take here X is equal to XL, so what will happen? What will happen for impedance? See here, Z is equal to root under Xc minus XL whole square plus R square. So if Xc is equal to XL, that is resonating condition, so this term will become 0. So Z is equal to root under R square. So we can R. So means current will be maximum. Current will become maximum when LCR circuit will behave as pure resistive circuit, because there is no Xc and XL, so that's why. So I hope you have understood this resonating condition. So uh, thank you for watching this. So in next video we will more discuss about the AC generator and AC generator as well as average power conditions. So thank you for watching our video. Thanks a lot.